Okay, we probably should get started. Jeff said people are probably studying for the midterm, which is why it's a little more empty today. Well in advance. That was a joke, by the way. It wasn't my joke, it was Jeff, so if it wasn't funny, you should blame him. We have a couple announcements. The first is that Michelle, the admin for this course, was sick yesterday, so she wasn't there to get your homework, so a bunch of people stuffed under her door. And we're going to consider any of those as just one late day. And if you wanted to turn in late homework yesterday and you weren't able to, you can turn it in essentially right now and we'll still consider it one late day. So if you turned it into one of the TAs this morning and you couldn't yesterday, or if you turn it in right now, we'll still consider it one late day. Okay, and the other announcement was, we have a feedback form that Jeff created and sent to all of you guys. It's a mid-semester feedback. We'd love to hear how you're finding the course so far, and if there's any things that you strongly dislike, and we can maybe remedy in the next, half the course or a third of the course, whatever's left. Okay, today we're going to talk about some uses of duality. I think this is going to be hopefully a fun lecture. We're also going to go fairly fast today, maybe not quite as fast as the last time. And if we have time left over at the end, which we may or may not, depending on, I guess, how fast we go and how many questions people ask, I'll go back and I'll just talk about polytopes and about polar sets, because I missed that last time, and I may as well at least walk you through it if we have time at the end. Okay, so today's about uses of duality. The one thing that's going to be key for this lecture that we learned last time is conjugate functions. I think they're going to be key from now on whenever we talk about duality pretty much. So I just wanted to remind you what we learned. If we have any function f, it doesn't need to be convex, just a function, then we can define its conjugate, which we denote by f star. And you have to be careful that you're reading that star to mean conjugate and not to mean the optimal value of f. I guess it's an asterisk when I mean conjugate, and if I mean the optimal value of a convex problem in which, or of a problem in which f is the criterion, I mean f star. So just make sure that you see the difference there. I agree, it's maybe that's a little bit confusing notation. But we take a function, we define this conjugate by the maximal inner product between y and x and f of x. So that's the difference between y transpose x and f of x maximized over all x. That's the conjugate function at y. And we talked about a bunch of properties of it. One nice property is that it's always convex. Even when f is not convex, it's always a convex function. And we talked about them particularly in the context of dual problems, because if we ever have an expression that looks like this, minimize f of x minus y transpose x over all x and Rn, then just by definition, that's the negative conjugate function at y. So this will pop up all the time when we're forming the dual function, when we minimize the Lagrangian over x, and that's where we get conjugates in dual programs. If f is closed and convex, then the conjugate of f is itself. That helped us say some things about, for example, what happens when you take the dual twice. And we have this property, which we'll use today. If x is a subgradient of the conjugate function at y, and that's true if and only if y is a subgradient of f at x, which is true if and only if x minimizes over all z, f of z minus y transpose z. Okay, so why is that true? Just to remind you, we talked about when we learned subgradient calculus, we learned that if we have a function and it satisfies a bunch of regularity conditions. Sounds like my mic just went off. Can everybody hear me okay? So I think the battery is dead on this mic. Could you replace the battery while I continue?
Yeah, sure.
It's right here.
Okay.
That's it. So if we Okay, we learned that when we take subgradients of maxima, if those functions are nice, if they obey some properties, and they happen to be satisfied in this case, then we can write the subgradient of, right, say the maximum of all these functions as the convex hull of the union of all points at which the maximum is achieved. So we can write this as f star y equals y transpose x minus f of x. Thanks, Jeff. Okay, so the mic should be back on now. Yay! So we write this as the convex hull of the subdifferentials of all the inner functions, and we take the subdifferentials over all points that achieve the maximum. And the subdifferential here is with respect to y, just like it is out here. So what's the subdifferential of this function with respect to y? It just gives us x. Right? So it's just this union. And now we can see, for example, if x is a point that minimizes f of x minus y transpose x, or it maximizes this, which means that we get equality here, then it's going to be in this union, so certainly it'll be in the subdifferential of f star at y. And the converse is also true. If a point's in here, then we can also prove that it's in, if x is in f star of y, then we can prove that it has to achieve the maximum, and therefore y is in the subgradient of f at x. Okay, so I'll leave you to check that at home. This comes from writing, for example, if we didn't know, for example, that it actually was one of these points, we could write x as, say, the sum of alpha I, xi, where each of these xi's satisfies, each of these xi's achieves the maximum. Right? And the alpha i's are non-negative and sum to 1. That's what it means to be in a convex hull. And then we can actually go ahead and prove that this achieves the maximum itself, and therefore y must be in the subgradient of f at x. So that's where that property came from. And it looks nice for strictly convex x, because if x is strictly convex, if f is strictly convex, then, for example, this problem here has a unique minimizer. Right, so I can actually write x equals the argument, because there's only one. And in that case, I'm telling you also that there's only one element of the subdifferential of f star, which means that f star, the conjugate, is differentiable. Right? If there's only one element of its subdifferential, that element must be its gradient. So we arrive at this conclusion. If f is strictly convex, then the gradient of the conjugate function at y is just exactly the point that minimizes, you could write it over x, that minimizes f of x minus y transpose x. Okay, so if I wanted to get a gradient of f star, I could solve a minimization problem, and it would tell me what a gradient is. So we talked about already two uses of duality, and we're going to elaborate on them today. I'll just remind you what we talked about so far. We talked about the idea of the duality gap. So if we have a point x that's primal feasible and a pair uv that's dual feasible, they satisfy the primal and dual constraints respectively, then this quantity, the difference between the primal criterion and the dual criterion, is called the duality gap between x and uv. And we have this upper bound that f of x minus the smallest it can get, f of x star over the feasible set. This is the primal optimal criterion value, is upper bounded by the duality gap. That's because the dual function is an upper bound on f star everywhere. So in particular, a zero duality gap implies optimality. Right? If I have a zero duality gap, then this is 0, so x is optimal. And the same is true with the dual problem. I can bound g minus g star by the duality gap, or I guess it's g star minus g, because I'm maximizing the dual problem. And if I ever get a zero duality gap, it implies dual optimality also. So we can use this as a stopping criterion in algorithms. Right? If I have an iterative algorithm that uses both primal, it tries to solve both the primal and dual problem, I can look at the duality gap and I can stop when that's small, and that guarantees me that the difference in criterion values is at least that small. This other important thing we talked about, and this is what we'll see some examples of shortly, is that under strong duality, so when there's a zero duality gap, if you have a dual optimal U star and V star, then you can just read off the stationarity condition for the KKT conditions, which we know must hold because of strong duality. And it tells us that x star, any primal solution, has to minimize the Lagrangian over x, over all x in Rn. So once we have the dual optimal U star and V star, we can now look at an unconstrained minimization problem, minimize the Lagrangian over all x, and we're told that any primal solution must satisfy that. It's not true that any solution of that is a primal solution, but we do know the first direction I mentioned. So that we can use this to characterize primal solutions. We can say that any primal solution must have a characteristic defined by the minimizers of this problem, and I'll present you some examples of that. If there happens to be only one minimizer of the Lagrangian at U star V star, then it is the primal solution, right? So that's another very nice case. So we can solve the primal problem from dual solutions. And if the dual happen to be a lot easier computationally, that's a really big advantage. Other questions? So here's an example. We're going to go through here's an outline. We're going to go through several examples of how to characterize primal solutions from dual solutions in a couple different statistics settings, statistics problems, and then we're going to talk about some algorithmic uses of the dual problem. In particular, we'll talk about dual gradient methods, which all stem from essentially this property that I told you here, that if we have the conjugate function, we can compute subgradients or gradients without actually having to form f star, right? Because we can just use f for that. And I'll talk about dual decomposition a bit and augmented Lagrangians. So just to say now, there are many more uses of duality that we could cover, but we don't want to spend too many lectures on duality. There's a lot of other stuff I want to cover too. But duality pops up all the time. So there's a dual simplex algorithm. We learned about the simplex algorithm. There's a very pretty dual simplex algorithm that goes along with that. There's something called dual smoothing, which you might get to as an advanced topic later on in the course. And in statistics, which is it's a very interesting use of duality because, as far as I can tell, this stuff doesn't really happen in other statistical theory. But if you want to sometimes prove that the solution of an optimization problem has a desired statistical property, you can actually use the dual problem to provide what's called a certificate for that. And it's a nice blending of statistics and optimization. So here's an example, a concrete example of how we might use the dual problem to characterize primal solutions. And it has some nice geometry involved too, so I thought I would share it. So we did this example last time with the Lasso problem and its dual. Right? So if I have the Lasso problem where I want to do sparse regression, here's its dual problem. We derived this last time. Okay, and I'll just write down the Lagrangian for you because we're going to need that to look at these stationarity conditions. So we started with the primal problem, which was this. And to derive its dual, to remind you, because this is unconstrained, I added a constraint, trivial constraint, and I swapped in a z for an x. So I actually swapped in a z for an ax here. And I just added the constraint that z has to be equal to x. Okay, so it's clearly the same problem. Thank you. That would have been clearly not the same problem. So this is clearly the same problem. And now I can write down this Lagrangian, which is a function of x and z, my primal variables, and u, the dual variable I introduced for this constraint. And that looks like this. And now I won't go through the steps because we did them last time, but if I minimize this over x and z, I basically get two conjugate functions. One is the conjugate function of the one norm, evaluated at A transpose u over lambda, and that gives us the indicator function of the L infinity norm ball. So that's where this constraint comes from. The other conjugate function had to do with this quadratic, and its conjugate ended up being another quadratic. And I got rid of some constants, and I flipped its sign to make it a minimization problem. So I minimized this over x and z, it gave me this problem, and then I transformed it to look like this. So according to the stationarity condition, if I have, say, u star, which is a dual solution, then if I take the subgradient of L over x and z, each of those blocks, any primal solution must have a zero subgradient when I evaluate it at the primal solution. So let's just go ahead and look at that. So what's the subgradient with respect to, say, the z block here? That's just the gradient, right, because it's differential with respect to z. And I get that z minus y plus u has to equal 0. U star has to equal 0. Okay, so at the solution z is ax. So what this tells me is that ax star is just equal to y minus u star. So that's the relationship between the primal and dual solutions. The primal fit, so the value of ax star, that's what I use to estimate y, is equal to y minus u star. And the other thing I get is that, so this is with respect to z. If I take the look at the subgradients with respect to x, then what does that tell me? I get that lambda times the subgradient of the L1 norm at x. So lambda times s, where s is the subgradient of the 1 norm at x, minus A transpose u equals 0. Right, so I'll just say that A transpose u is equal to lambda times s, where s is subgradient of the 1 norm at x star. So that's what happens at the solutions also. So I've written that down here just in a little different on the slide. I said that each component of this vector, right, is a subgradient of the ith component of x star. So it's equal to lambda if x star is positive in that coordinate, minus lambda if it's negative, and it can be anything between minus lambda and lambda if xi is 0. So this is a relationship between the primal and dual variables. So what can we learn from this? If we look at this directly and we see, if it so happens that I solve the dual problem and I take the inner product of the dual variable with the ith column of A, and I see is that less than lambda, if that's true, then this implies that the ith component of x at the solution must be 0. Right? Because it tells me that, well, I'm in this case, because it's the only case where it can be strictly between minus lambda and lambda, and that can only happen if xi is 0 in that component. So that's a nice relationship between the primal and the dual. These are both nice relationships. So now if I look at the dual problem, I can see something directly, which is trivial from looking at the dual problem, but from the primal problem it's not so obvious. So the dual problem looks like this. And I'm just going to call this set C. So I'm going to write this as U is in C. And C is going to be equal to the set of all U, for which, maybe the set of all V, just so not to confuse you, such that A transpose V in infinity norm is smaller than or equal to lambda. Okay, so this is just I'm rewriting the constraint as if it's in C. So what is it? It's minimize y minus u in norm squared subject to u being in C. Well, the solution, we know, just by definition of what a projection is the projection of y onto the set C. Right? So what does that tell us now that we know that AX star is equal to Y minus U star? That tells us that the lasso fit is I minus the projection onto C of Y. So it's the residual from projecting onto the set C. And what's C? C we can actually write as the intersection from I equals 1 to P of two things: the set of all U such that AI transpose U is bigger than or equal to lambda, and the set of all U for which AI transpose U is, that should be less than or equal to lambda, and bigger than or equal to minus lambda. Right? Because if I put these two together, this tells me that the absolute value has to be less than or equal to lambda. And if I take the intersection, I get that it's less than or equal to lambda for all coordinates. And therefore, we know C is actually just a polyhedron. Right? It's an intersection of half spaces. So just in like 2 lines from the dual, I've established that the lasso fit is the residual from projecting Y onto a polyhedron. What's the polyhedron? It's this. That's very non-obvious from looking at the lasso problem. Right? If you look at this primal problem up there, that's not a very obvious statement, but it came out just from the dual in the primal dual relationship. Okay, so what does that do from us besides being interesting? It actually allows us to say a bunch of things. Once we use a little bit of geometry, we can make a bunch of statements now leveraging this fact. So I've drawn this picture up here. I guess I'm not going to try to recreate it on the piece of paper here because I'm not very good at drawing. So I'll just try to point to the picture. So on the right-hand side of the picture, we have RP. Okay, and we're imagining a hypercube in RP. So that's the set of all V in RP that have infinity norms smaller than or equal to lambda. So it's a hypercube. It's the L infinity norm ball of radius lambda. And this polyhedron that we wrote down, we can think of C as the inverse image of that hypercube under the linear map A transpose. So let's just be clear. C is equal to the set of all U such that A transpose U is less than or equal to lambda. In other words, it's the set of all U such that A transpose U is in the set V such that the infinity norm as V is less than or equal to lambda. Right, so I can think about this. I don't mean a matrix inverse. I mean actually the inverse image just under the function A transpose of the hypercube. Okay, so that's what that arrow is doing there. It's going from the hypercube in RP to something in Rn, and that something is a polyhedron. So I drew this polyhedron here. And if we have a point Y at the top, then we take Y and we project it onto this polyhedron. Right? That's what I studied, and the projected point gives us the dual solution, and the residual from that projection gives us A times X star, the lasso fit. So this is just what we learned, but on the picture. So now we can read off a bunch of properties. So the first property that we can read off is that if I think about the lasso fit as a function of Y, it's non-expansive. That means that if I have the solution at Y and the solution at Y prime, then the norm difference between AX star at Y and at Y prime is at most as big as the difference between Y and Y prime. So why is that? That's just a property of projection onto convex sets. So we can just draw ourselves a picture. If I have any set that's convex, then you can convince yourself, and you can try to prove it if you want, that if I project a point Y into the convex set, and I project a point Y prime onto the convex set, then the difference between the projected points, this distance can be no longer than the original difference. The original distance, excuse me. And if it happened to be larger, then I had to have something non-convex. Right? If this is my set I was projecting onto, and happened that the distance was larger, then it has to be something non-convex. So this is a nice perturbation result for the lasso. Just tells us that if you give me a Y prime, I can tell you immediately that my fit's not going to change any more than the difference from the data points that I observed. So what else do we see from this picture? If we go to the right-hand side in RP, every face of that hypercube corresponds to a particular active set of Lasso solutions. And that's because I'm imagining what's over there as, say, the dual solution. And I know that if the dual solution is strictly less than lambda, then that implies that that component of the primal solution is going to be equal to 0. Right? So I'm imagining that every face of that hypercube corresponds to a particular active set of Lasso solutions. And if I look at what happens to that face under linear transformation, that means that every face of this polyhedron also corresponds to a particular active set of Lasso solutions. So I've just drawn in bold, say that the upper face there on this polyhedron corresponds to that face that I drew in bold in the hypercube. So that means that if I have a point y and it projects to a face, then that face determines its active set. So here's another conclusion we can draw, and again, I'm just arguing kind of intuitively here. If I take this point y and I move it a bit, it's going to project to the same face. Right? So I'll just draw that on the picture. If I have y and I just move it a bit in any direction, it'll project to the same face of the polyhedron. Right? So it's not going to, if I move y in any direction, it's going to project to the same face. That's not going to be true if y lies on one of these rays. Right? Because if I'm one of these rays and I move it this way, I'll project to this face. And if I move it this way, I'll project it to this face. Okay, it's a vertex in R2, but it's a face generally, and they're not the same thing. So unless y lies on one of these rays coming out of the corners, if I move it a bit, it's going to project to the same face, which means that if I perturb the data a bit, I'm going to get the same active set when I run the Lasso program. So all of these rays here, they comprise a set of Lebesgue measure 0 because they're like lower dimensional things, and there's a finite number of them. So therefore, I can argue that for almost every y, if I take a small perturbation of y, it's going to project to the same face, and therefore the active set is going to be the same. So we've just established that the Lasso active set is locally constant. I take little perturbations of y, the active set doesn't change almost everywhere. So if y is a density, it happens with probability 1. And more so than that, the Lasso is a locally affine projection map. Right? Because locally, it's just projecting onto a face, which is like an affine space. So a bunch of stuff that, all these, if you see all these properties written down, you would think that they would be very difficult to prove. And I did kind of wave my hands a bit, but they come from the dual problem. They just come from the dual problem in some geometry. Questions about that? More up? More?
A little bit more. I'm unclear how you derive that AX star is equal to y minus y star.
Oh, that was from the stationarity conditions. So I wrote them down here. So we had the Lagrangian here. Remember, and we know that with respect to all the primal variables, we have to have a 0 subgradient. So I took it with respect to the z block of primal variables, and with respect to the x block of primal variables, and they gave me two different conditions. And with respect to the z block, it just gave me the fact that ax star was equal to y minus u star. So I just took the gradient with respect to z, and I substituted in z equals ax as the solution.
Derived.
What's that?
It's a derived property.
Yeah, right. It comes from the primal dual relationship. I mean, that is the primal dual relationship. It comes from the KKT conditions. That was an example of how we might use that, even though we can't infer what x star is. Right? We know that ax star equals y minus u star. We can't infer what x star is because if A is column rank deficient, there's a ton of solutions to that linear equation. There's an infinite number, and not every one of them is a Lasso solution. But we can use this to characterize Lasso solutions in this way right here. We use it to characterize all these properties of Lasso solutions. Question?
Can you say a little bit more of the pictures where the infinite ball, what does the face correspond to? Did you say the face projected to the face on the left-hand side?
Yeah, right.
So what is the face of the infinite ball correspond to?
This, so we can think about it in a couple ways. I said it slightly differently, but we can think about it like this. Each one of these faces has the property that, if I look at the way it's defined, right? Or did I write down the polytope? Or the polyhedron? I wrote down here. So faces of this, or of this, are going to be defined by a set of i's for which these are tight. So AI transpose U equals lambda, or AI transpose U equals minus lambda. So that actually defines an active set, because it tells us that a bunch of AI transpose U's are smaller than lambda strictly, and we know from this property that we derive from the stationarity condition, that implies that xi is 0 at the solution. So faces of this polytope here, or polyhedron, I shouldn't call it a polytope because it's not necessarily bounded, of this polyhedron correspond to a particular active set. And I can think about, if I take then the A transpose image going this way, that means that faces of the L infinity ball here also correspond to a particular active set. They also correspond to a set of signs, because right, I actually specify AI transpose U equals lambda or minus lambda, and that specifies the sign of the non-zero variable as well. So if I tell you a set of active variables, or of non-zero variables S, and their signs, that tells me which face you're on.
So what happened is A is not invertible?
A is not invertible, necessarily. This doesn't mean the inverse of A transpose. I'm thinking of A transpose as a linear map that goes from Rn to Rp. And A transpose inverse, I'm just thinking of as the inverse image of a function. So if I have any function f, and it goes from A to B, whether or not it's invertible, I can talk about its inverse image of some subset C as the set of all x in A, such that f of x is in C. So it's the inverse image of something in B, in which case here is Rp. So I take the inverse image of the L infinity ball, it gives me something, which is itself a polyhedron. Yeah, questions?
Why is projection always on the contour of that polyhedron? So does that mean X solution always is kind of contour always in the cube?
So I didn't quite understand the question. So y always projects to something on the boundary. That's true. Unless y happened to be in the interior. If I observed y in here, then it would project to itself.
Yeah, so X also, the solution of X also projects to the corresponding part in RP. So that means X is always have the norm less than equal to.
I don't quite follow that, no. So I know that AX star is this vector that points from U star to Y. So that's what I know. I don't know anything about X. I know something about AX. And I don't know anything about projection onto this cube. I just know something about projection in this space. Maybe you could ask me after class if you still have a question.
Is there any relationship between the axes of function?
Yeah, that's a great question. I don't know the answer to that, actually. I thought about that. But so the question was, how does this face and that face differ in terms of their active set? And intuitively, you'd expect that they differ by, if they differ by dimension 1, right? If one is a k face, the other one is a k minus 1 face, you'd think that they differ just by one variable. But geometry can be very tricky. And what can happen is, if p is a lot larger than n, then a lot of the faces on this cube can actually project to the interior of that polyhedron. So they never appear on the boundary. So it's much more complicated to answer that question, which faces are neighbors of each other. Because it could be the case that, say, this face projects to the boundary, but its neighboring face projects to the interior. We never see it on this polyhedron. So this could have a lot less faces than the hypercube.
If you were to project into this polyhedron, and you did find that you started if it wasn't that boundary or that was a projection, how would you characterize the rest of the affine set?
The rest of the affine set here?
Of that?
Yeah, another good question. So I didn't have time to write it down, but it's defined by the matrix A, the active set S, and the signs little s, and lambda. Once I know those things, I can write out an equation for you for the affine space. It happens to be, I might be misquoting this. So I think it's something like the null space of AS transpose. That's the linear part, and then there's an affine part that depends on lambda and AS transpose and little s. But this is like the linear part of the space, and this is like the translation. Something like this. But I may have some transposes mixed up or something. I don't perfectly remember. But again, it comes from, it comes in part from studying the KKT conditions. A lot of good questions. Okay, so we just learned a bunch of stuff about the lasso from the dual, and there's a bunch of papers that try to do this, and I want to share with you a particularly cool result that is pretty recent. It was 2 years ago. And this paper talked about something called safe rules, which has become, I think, kind of a small but active area of research now in sparse learning problems, not just for like regression, but for a bunch of different problems. So the idea is that if I have a huge, huge data set, and I have a value of lambda, the question is there a way, before I actually solve the convex problem, to eliminate some features from the problem a priori? So can I say, before I even solve it, that all these features will have a zero coefficient? I know for sure. And therefore, I can exclude them from the optimization problem. Sounds like impossible, right? Sounds like that's cheating or something. But actually, this paper provides a way to do it. And it's very important to emphasize this is not an if and only if statement. I can't tell you all the features that will be zero, but I can tell you a subset of the features that will be zero. And of course, then in practice, the question is, how many of them can you exclude? Is it useful enough in practice that you'd actually use it? And for different problems, there are different performances, but for a lot of problems, it's very useful at excluding a good fraction of predictors. So it's a nice pre-screening to apply to your optimization problem if you're doing something with the one norm and you're trying to induce sparsity. So we're just going to talk about it for the lasso, but this paper also talks about it for logistic regression and for one norm SVMs. A little bit more complicated for those cases, and we haven't talked about them, so I'm not going to talk about that. But here's the reference in case you're interested. So the paper claims that I can write down this rule on the slide, that before I solve the problem, I can take the ith predictor, look at its inner product with y, and if that happens to be smaller than, this should be an absolute value, by the way. If that happens, if an absolute value, it's smaller than lambda minus the norm of a, I, times the norm of y, times some function of lambda, where lambda max is defined as the largest coordinate of lambda that gives me 0 in all of the components of the lasso solution. So it's actually just this right here. So let's just see for a second if we can figure out where that comes from. If lambda is equal to A transpose U in infinity norm, then the claim is that x star is 0, the Lasso solution. So where does that come from? Once again, it comes from the dual, right? Because if I put lambda equals A transpose y, then the dual solution is equal to y, right? Because that satisfies the constraint, and I get y minus y is 0 norm. So that's the dual solution, u equals y. And then what's the primal solution? It's ax equals 0. Okay, so I can just take x star equals 0, because that's going to minimize the criterion as well. So that statement that this value of lambda was the smallest value of lambda for which all components of the solution were 0 also came from the dual. So if I do this rule, and it so happens that an absolute value of ai transpose y is smaller than the right-hand side, I can say that at the solution xi star is going to be 0. And I can remove the ith column of A, and I can just do the problem on A with one smaller column. So it's like a linear pass over the feature set, and I throw out a bunch of features. So its construction, we'll kind of quickly go over it. Its construction comes from the Lasso dual problem, which is why I'm presenting it in class today. So the dual problem is like this, where I've just actually written it in the form where it's a maximization problem, and this was what the criterion looked like before I got rid of the constants. It's the norm of y squared minus the norm of y minus u squared over 2. So we start off by saying, let's suppose that u0 is a dual feasible point. So I just had any point that satisfied these constraints. And for example, I could take y and I could scale it by lambda over lambda max. And that would give me something that satisfies the constraints. Then if I look at the value of the criterion at u0, that actually provides me a lower bound for the dual optimal value. Right, I'm doing a maximization problem, so I can lower bound it by just evaluating at a feasible point. So I can add that as a constraint to the problem. It doesn't change anything. So I can maximize g subject to these constraints, and I can add in the constraint that g has to be bigger than or equal to gamma, where gamma was the value at the feasible point. Okay, so I've not really done much now. But here's where the interesting part comes. Now I think about computing the maximum of AI transpose u subject to g of u being bigger than or equal to gamma. And I also think about computing the minimum of AI transpose u subject to gu being bigger than or equal to gamma. And let's suppose I could do this, and I called the maximum of these two values mi. So it's the maximum value I obtain from either of these optimization problems. Or in other words, it's the maximum of the absolute value of AI transpose u subject to g of u being bigger than or equal to gamma. So now I know that if mi is less than lambda, then certainly at the dual solution, AI transpose u star has to be strictly less than lambda. Right? Because if within the constraint set I can't find any u that makes AI transpose u equal to lambda in absolute value, then certainly at the solution that can't be true, because I'm minimizing over that constraint set. Okay, but that in turn, from the KKT conditions, when we looked at the stationarity condition, it implied, remember we just talked about this a few slides ago, that the ith component of the Lasso solution is 0. So if I can actually solve these problems, and the solution happens to be smaller than lambda, I can throw out the ith variable from the Lasso problem successfully. And using another dual argument, we can actually solve these problems explicitly. We can look at their duals, and we can get an explicit form for what those maxima are going to be in terms of a and y and lambda. And we can write the rule mi is less than lambda exactly as the safe rule I wrote down for you on the previous slide. So this is a rule in terms of right in terms of a, y, lambda, and lambda max. So that's very cool. I just want to briefly say that for other problems, so even for problems where we can't do this explicitly, we can't write a closed form for that maximum, that's true for logistic regression and for one-norm SVMs, we can upper bound these maxima, or we can upper bound these problems in some way, or we can even try computing it analytically, and then we can use that rule to throw out features. So if I upper bound the solution, then upper bound is still less than lambda, then mi is less than lambda, then I can throw it out. Or if I just try to do it by bisection, if it's a one-dimensional problem, or if I try to do it by some convex method and I get an answer and it's less than lambda, then it's not an explicit closed form rule, but if that optimization problem was cheaper than solving the original problem, I might as well do that, and I can throw out features ahead of time. So it applies to a bunch of other problems. But the Lasso is the case in which it's the simplest as a closed form. Did you have a question? That was it. Okay. So here's a picture of what it's doing. It comes from the paper. I'll just briefly try to explain what this crazy-looking figure is displaying. So if that, let's say that red point is equal to y, or sorry, is equal to the dual solution. Let's say this red point is equal to the dual solution. And now I look at contours of G. Right, so that makes no sense. I said this is the dual solution, right, where it projects onto this polyhedron. And now I look at contours of G, bigger contours. If I find a feasible point, so here's a feasible point. It's not necessarily the optimum, but it's a feasible point. Then this defines some elliptical region for the Lasso criterion, because that's a quadratic G, for which we know that the solution has to lie in this elliptical region. Then I go ahead and I look at the kind of like the affine spaces defined by each of the constraints. And if they don't intersect this elliptical region, So I know that at the solution, it certainly cannot lie on that face. It has to lie in the interior with respect to this inequality. So I can throw out that feature completely. So I just go through, I cycle through, and I try to look which of these constraints are going to intersect this elliptical region. And if it doesn't, too bad, I'll just throw out the feature for that particular I. Okay, so here's another example, and it looks very similar to the Lasso, but it's a very different problem in terms of some of the primal properties, like how easy it is to compute, but the duals look very similar, which is why I wanted to present it. So if we consider something like a reverse Lasso problem, so now instead of having a matrix A here, I put a matrix D here. This is sometimes called one-norm analysis, another name for it. We consider D here a given matrix, just like we're given covariates. I might be given some penalty matrix D, and I'd like to solve this problem. And you cannot turn this into a Lasso problem if the rank of D is strictly smaller than its number of rows. So if D was invertible, I could just put a D inverse here, right, and reparameterize. It'd be a Lasso problem. But if D is row rank deficient, I can't do that. And they're actually very different problems. So we can just think off the top of our head, why is this more complicated to solve than something like Lasso? So what happens if we did generalized grading here? If we tried to make this the smooth part and that the non-smooth part? So what would the prox function be if this was H? It would be that, right? So we'd be doing nothing because the prox function would be the problem. So there's no luck there. So in many ways, because we have a linear transformation kind of intertwined with this non-differentiable part of our objective, this is a lot harder. But the duals look similar, and the duals kind of reveal that this problem has a lot of the same properties of the Lasso. So the idea behind why you ever want to solve this problem, before we talk about its dual, is that if you had a problem in which you wanted some particular type of structure in the solution, you might be able to choose the penalty matrix D so that sparsity of dx star implies some structure in x star. So let's go through a very simple example just on our paper. What happens if we wanted to, say we observed a bunch of points, and they were ordered from 1 to n, and each of these was, say, yi, and they looked like this. We order them as a signal because they came to us with some inherent signal, and they look something like this. So I believe that, if you can't see that there's some piecewise constant signal that's underlying my observations, and yi were distributed with maybe some Gaussian symmetric noise around this piecewise constant signal. So in this case, I want the solution of my optimization problem to estimate this piecewise constant function. So how would I do that? By setting it up like this. Well, I could choose D so that in each row there was a -1 and a 1, and it went down like this in this bidiagonal fashion. So that means that dx is equal to, in one norm, is equal to the sum of the differences between xi and xi plus 1. Right? So if this is sparse, it means that if dx is sparse, it means that a lot of these differences are 0. So that means that I'm in a constant region. Right? If there's 0 for some contiguous block, I'm in a constant region. Where it's non-zero, I can get a jump. So if it's sparse and only has 3 non-zeros, that defines a piecewise constant function with 3 jumps, or 3 breakpoints. Okay, so that's just an example of where, if we want a particular structure, we might think about what kind of D would give us that structure and solve this problem. So I'm just going to give you a couple more examples of choosing Ds. And this problem is a type of problem called fused Lasso problem, and it's also called total variation denoising in the signal processing literature. And generally, we can think about, for this class of problems, choosing a graph over our observations. So the nodes are the set 1 through n. I should have put an n there. I guess x should be an Rn here, because y is an Rn. So the nodes on the graph is a set 1 through n. And we're going to think about picking some set of edges to define a graph over those nodes. And we're going to minimize dx in one norm, which is we're going to go up and we're going to sum the absolute difference between nodes that are connected by edges. That's how I'm going to think about defining D. So it's just the extension of this idea to different graphs. This was the chain graph, right, where I had just an edge connecting each one of these points to its adjacent neighbor on this line. So here's an example. I took this original image. I made a C for Carnegie Mellon, and I gave it 4 colors. So in terms of the underlying representation, it really only has 4 numbers. And I just defined a color scale at each one of those numbers. So green is for 0, blue is for 1, I think this is for, pink is for 3, and red is for 4. And then I took that image and I smoothed it and I added a bunch of noise. And this is the middle image right here. It's a noisy version. So in image denoising, I want to find a piecewise constant image, so blocks of colors, that best approximates this noisy version in some way. So how I did that in this case is I defined a graph where I connected every pixel in the image to both its neighbor horizontally and its neighbor vertically. So this was y. I strung it out into a huge vector. And then I connected components of y that corresponded to adjacent pixels in the image horizontally and vertically by edges in this graph that I constructed. And then I ran the fused lasso over that 2D grid, and I got this solution for some value of lambda. And you can see because the true image was piecewise constant, it did a pretty good job of capturing the true structure. It's not perfect, but it's pretty good, especially considering how noisy the image was. Okay, I'm going to skip this example. You can do it on arbitrary graphs. So here's an example where I did it on a graph defined by states in the US on a real data set. So using the same steps we did in the Lasso, we can derive the dual for this problem. I'll just write down for you what the substitution will look like, and then you can go through and check it at home. So this is the criterion, and I just rewrite this criterion as I add this variable z in the one norm part, and then I do z equals dx. Okay? And when I derive the dual of this, I get this problem here. And looking at this problem, I can also talk about a primal dual relationship. It looks pretty similar to the Lasso. And I can also talk about projection onto a polyhedron. And I get basically the same picture. I just changed all the labels, but the same picture as we had before, and all the same properties. So I can say all the same things. You know, if I perturb y a bit, then the structure of the solution won't change much. Not the support, but which entries of dx are going to be equal to 0 is not going to change. It'll be locally constant almost everywhere. Okay, so the same arguments apply here. And I'm running a little bit short on time for this section, so I'm just going to skip them, because we've seen all of them. But I do want to point out one other thing, which is going to lead into what we're talking about next in some sense, and also maybe what we continue to talk about throughout the course, is that if we look at the dual here, it's disentangled the relationship of the linear operator D with the non-smooth part. The non-smooth part here is the infinity norm of U. So if you ask me now what the prox function for this problem is, it's very easy, right? The prox function is I want to find, if you give me well, maybe I shouldn't use y, just not to confuse you. But the prox function looks like this. Find the u that minimizes this over all u. Find the u that minimizes this for a given z. That's the prox function at z. Okay, because usually I have something like a plus h here, but h is an indicator function, so I can just write it as a constraint. This prox function is very easy, right? If it ever happens to be outside of the L infinity ball for that coordinate, I just push it to lambda or to minus lambda, whatever side it's on. And otherwise, I just return zi in that coordinate. So we can do generalized gradient very easily for this problem. And that means we can get a primal solution. Because if you look actually at the primal dual relationship, when I derived it, actually tell me that uniquely the primal solution is y minus d transpose u star. Okay, so in this case, this is an actual example where the dual is a lot easier to solve than the primal, and I can do it with one of the methods we've learned so far. Okay, let's take a short break and we'll come back and talk about dual methods. Okay, so we're going to talk about dual gradient methods in the last 20 minutes of class. And next time you're going to learn, one of the things you'll learn is kind of like the conclusion of this lecture, which is I'm going to present for you one set of methods that are nice for one reason but bad for another reason, and another set of methods that are nice for one reason but bad for another reason. I'm going to say that we can't combine them, and the next time you're going to try to combine them into an algorithm. And next lecture is going to be taught by one of your TAs, Aditya. So let's get this topic started. So all the examples we looked at so far, we've had cases in which we can derive the dual, which amounted in most cases to deriving conjugate functions in closed form. But there was a question last time in class, and I'm sure people were wondering this. What happens if we can't write the dual in closed form, write the conjugate in closed form, but we still want to use the primal dual relationship? Are we stuck there, or can we still use the dual in some way? And it turns out we can use the dual. And that's what these next few slides will be about. So let's consider this problem as an example. Let's suppose we just have minimize this convex function f subject to the constraint ax equals b. Okay, so I think we might have gone through this in class, but if we didn't, then just make sure you understand why this is true. Here's the primal problem. The Lagrangian is f of x plus u transpose ax minus b. Okay, and if I minimize this over x, I get the conjugate function, and I get a minus b transpose u, and that's exactly where this dual problem comes from. So if we define G to be minus the conjugate of f at minus A transpose U, that's the criterion in the dual problem, then if I ask you what its subgradients are, suppose we want to do something like subgradient ascent in the dual because it's a maximization problem, but we didn't know what f star was. That's the situation we're in. Subgradients of G from the subgradient calculus rule, right, I take minus the transpose of the linear combination, of the linear transformation there. Yeah, so, okay. I think did I write this? I did write it correctly on the slide. Let's define G to be just the conjugate, not the minus conjugate, because now G is convex. Right, because minus this would have been concave. So I do want to talk about subgradients of a convex function. And what are its subgradients? I take this transpose, so it ends up just being A, times the subgradients of f star, A transpose U. That's a prescription for what the subgradients of my dual criterion are. And remember we had this rule from studying conjugates that told us that a point x is in, say, the subgradient of the conjugate function at minus A transpose U, if and only if x is in the set of minimizers of f of minus A transpose U, I'm sorry, f of z minus this transpose x, so it ends up being plus u transpose ax over all z. I don't want to keep using x. That's supposed to be z. Okay, so this is true if and only if x is in the set of these minimizers. Right? That's how we characterized the subdifferential of the conjugate function. So that means that if I can find a point x that minimizes this, then I can take minus A times x, and that's the subgradient of G at U, right? Because I wrote it in the last slide. I'll just write it up here to repeat it. Subdifferential of GU is minus A times the subdifferential of f of minus A transpose U. Okay, so once I have a subgradient of this, I can multiply it by minus A, and I get a subgradient of the dual criterion. Thank you. Okay, so then I could do something like subgradient ascent on the dual. Because if I can solve this problem, I take AX, that gives me a subgradient, and now I can apply subgradient ascent, because that's something we've learned. So what do the steps look like? Right, I just start with an initial guess for the dual variable, u0, and the update is going to look like compute x k to be, right, it's going to minimize this when I evaluate it at my current u, because I want to compute a subgradient at uk. I first minimize this problem. Then AXK is a subgradient, or rather minus AXK is a subgradient. So then the update step is going to look like I take my current u and I subtract off a step size times a subgradient at uk, which was this, right? And then I actually left out one part of the dual criterion, which was this minus b transpose u, but its subgradient is just b, right? So I have to put that in here too. Ends up being a plus b. So I can just write that like this. uk plus tk times ax k minus b. Okay, so it's written up more neatly on the slide. I solve a minimization problem involving f. There's no f stars. No duals need to be computed. I do a subgradient update step, and I repeat them. So some people call this the dual subgradient method or dual ascent. And we're going to see it as a pretty natural interpretation for a bunch of different problems. But the nice thing, the reason we like it now is that there's no f stars anywhere. We need to know the conjugate function in order to do this. So we can do it even if we don't know the dual and closed form. So if f is strictly convex, then f star, the conjugate, ends up being differentiable. Right? We talked about that at the start because this minimizer is unique. So there's only one subgradient, and it's the gradient. So in that case, we get dual gradient ascent. I just rewrote it. There's no reason why I had to rewrite it, but I just rewrote it just to emphasize that if the primal problem happened to be strictly convex, then we actually have a gradient update in the dual rather than just a subgradient update. So I'm not going to cover this. You can go through it on your own. But in fact, if f is strongly convex with a certain parameter, d, remember what that was from our lectures on gradient ascent, that actually implies that not only is f differentiable, f star differentiable, but it's Lipschitz. The gradient's Lipschitz, and it has parameter 1 over d. Okay, so here's a proof of that. So strictly convex implies f star differentiable. Strongly convex implies the gradient of f star is Lipschitz. And remember, we like this condition with gradient methods because if we knew it's Lipschitz constant, we could take 1 over that, and if we took a step size less than that, we got a 1 over k rate of convergence. And we are guaranteed convergence. Okay, so I just summarized that here. If f is strongly convex with parameter d, then dual gradient ascent with constant step size, t less than or equal to 1 over its Lipschitz constant, which is 1 over d, converges at a certain rate, 1 over k. So that's, so far, not a bad result. But if you think about the assumptions that led to that, that's completely different from gradient descent. Right, here I had to actually assume that f was strongly convex with a certain parameter, and that gave us a rate of 1 over k. In gradient descent, if I assume that f was strongly convex, we got exponential convergence. So there's a huge difference between those two rates. So this is a pretty strong assumption that leads to a modest rate. And I'm not going to cover them, but if you're interested, you can look them up. Dual generalized gradient ascent and accelerated dual generalized gradient method, they carry through in the same manner. So there's a similar setup for applying generalized gradient and acceleration in this framework. So what are the disadvantages of dual methods? I kind of mentioned them already. They can be slow to converge. So if you think of subgradient method, right, if I have f that's convex, in general, I am just doing subgradient ascent in the dual. That's what I'm doing. Unless f is strictly convex, I'm doing subgradient method. That's pretty slow to converge. Even with pretty strong assumptions, like strongly convex, I still get a 1 over k rate. So it's not a very fast method. Another disadvantage is that it has poor convergence properties. So even though we're talking about achieving convergence here, we're talking about convergence in the criterion. So the dual criterion converges to the optimal dual criterion, which means that the primal criterion is also going to converge to the optimal primal criterion because of strong duality. But we're not talking about convergence of the actual iterates u or x. And in this problem, it's actually important because I might not even end up in the limit a point x that's primal feasible. So if I repeat these, I'm not guaranteed that u is going to converge to the dual solution. I'm guaranteed that f of u is going to, or g of u is going to converge to the dual criterion, but not that u itself will, unless I have much stronger assumptions. Which means that I don't even know that I'm doing the right update step for the primal variable. It might not even be feasible in the limit. So it doesn't have very good convergence properties. But it has one big advantage, and that's decomposability. Okay, so we're going to stress this now, and like I said, we'll get back to decomposability next time, but dual decomposition is also a pretty neat application of duality. It's very simple. So if I have a problem in the that decomposes into blocks of variables, so minimizing the sum of f of xi for a block of variables xi, subject to this constraint ax equals b, then it actually decomposes in the dual. If I didn't have this constraint in the primal, I could decompose it. I could solve it over every block of variables separately. But this is a complicating constraint. It ties all the variables together. But in the dual, it actually separates nicely. So we're just going to exactly proceed like we did here, where we're going to minimize f of x plus u transpose ax. Right, so what's that? Here f is a sum, so it's the sum of fi xi plus u transpose ax. But you can see that if I decompose the columns of A according to the blocks of my variable, that actually decomposes into B separate minimization problems, one for each block. Right? Because I can write this as a sum also. The sum of, I can write U transpose AX as the sum of U AI transpose XI. So then and now each of these sums only depends on Xi, and I can split it up into B different minimization problems. So that's the big advantage of these dual methods, is that we can parallelize a lot of problems that you couldn't parallelize in the primal. So here's the dual algorithm. Instead of minimizing this globally, I minimize it separate for each block of variables, and then I gather them all into the update step for U. So you can think of this as a broadcast step and a gather step. The first step, when I'm doing this minimization, I have to send U to each of the B processors that I'm doing the minimization. So in this picture, maybe I have U at the center, and I'm sending U out to each of these processors. It solves its own minimization problem, independent of each other. And then when they're done, they send X back to the center. That's the gather step, and we update U, the global dual variable. So one global dual variable, and we split up the primal variable into a bunch of blocks. Here's an example with inequality constraints, and you can do it with more general constraints too, as long as the constraints can be, in some sense, split up across units. So we're running out of time. I guess not to be unexpected, but I'm going to have to skip the interpretation. Maybe, Aditya, you can go over this next time, what the interpretation of the decomposability is in terms of price coordination, because it's a nice one. But I need to get to this because that's going to set up where we're going next time. So the convergence of these dual methods, they can be greatly improved if we add something to the primal criterion. And that's called augmenting the Lagrangian. And it's a very simple idea. It actually improves convergence by a big deal. So if I start with this primal problem, the same one I had before, minimize f of x subject to ax equals b, I can add this term to the criterion, and it won't do anything, right? Because at the solution, ax is equal to b, or that's the constraint set, so this term is 0. So it's not doing anything, not changing the problem, but it's actually going to change the dual if we go out and write the dual, and therefore it's going to give us a different algorithm. So if we assume that, for example, A has full column rank, then this is strongly convex, this whole criterion, because this part is strongly convex. So I didn't need a nice f. I'm just making it nice by adding this term. And therefore, I have that the objective function, the dual objective function, is differentiable. So it kind of helped me out by smoothing out my function. And I can use dual gradient ascent. And I'm going to repeat these steps. It's the same as before. But remember, this is also part of the criterion, so I have to add that part in now. So the advantage, I'm just going to talk about the advantage, is that we get much better convergence properties. Okay, so we can, for reasons kind of beyond what we've learned so far, we can say that this converges a lot faster in a lot more situations than just the standard dual gradient method. And I mean, you can already see why that would be true, right? Because for any f, it doesn't matter. As long as A has full column rank, the criterion is strictly convex. So I already have that it's that the conjugate's differentiable and that its gradient's Lipschitz, and I can already apply the arguments that we did for gradient ascent to get the 1 over k rate. Okay, so I didn't need a nice f for that to happen. And generally, we can put less strong assumptions on f to get good convergence here. But the disadvantage is decomposability, right? Because if I had a problem that, suppose f decomposed into a block of a bunch of different things, then by adding this rho over 2 times ax squared minus ax minus b squared term, I've disentangled those blocks. So it's no longer decomposable. So I've sacrificed decomposability for good convergence. So those two things, when we talk about augmented Lagrangians and dual methods, are kind of at odds. And what we'll talk about next time is something called, or a detail we'll talk about for a little bit, something called ADMM, the alternating direction method of multipliers, and it tries to combine the best of both worlds. It tries to get the decomposability of the dual methods with the good convergence property of the augmented Lagrangian methods. Okay, that's it, and have a good weekend. See you on Tuesday.